All right. Welcome, everybody, to the third episode of Science Unplugged. We've had great success doing this show, and we are thrilled that this is going to be a routine weekly show for you guys every Thursday, except we're going on hiatus already. We've only had 3 episodes. We're going on hiatus till the new year, and I'm just going to put it out here ahead of time that our next episode is going to be on January 21st because we are lining up a whole slew of different scientists and graduate students of varieties of different fields of science to talk to you guys. So it's going to be a lot of fun, and stay tuned, and we hope that you will join us in the new year. Also, we will be switching. Can you chat about quantum mechanics? Let's not jump the gun just yet, but we may be able to help you tonight. But one thing I also want you to do is, if you see here on one of the cam slots, we have our producer, Val, and she is under the Alan Alda Center headline there. So I want you guys to follow her on Blab, follow her on Twitter, because we are going to be doing our broadcasts in the future from the Alan Alda Center webpage through their Twitter account. So when you see the countdown timer and you're going to subscribe to the show, you're going to subscribe to it under the Alan Alda account. So let me introduce myself. You heard our new intro music. We have Science Unplugged intro music now. I'm Peter Chahales. I've been the host of Science Unplugged. That's right. Tell a little bird, tweet us out, share us on Facebook, tell your mother, tell your grandmother, your father, your best friend, your neighbor, do whatever, create smoke signals, send a carrier pigeon, do whatever you need to do to get the word out there, because we want this to be your #1 stop for science on Blab. So I am very excited today that actually I have a co-host today. So you guys may remember Stephen Jaret from my first episode of Science Unplugged. Stephen, how are you?
Very good.
Good to have you here. And the way it's going to work in the future is that Stephen and I are actually going to be rotating hosting duties here, because we want you to really get the perspective of many different scientists. We don't need to just hear my loud voice all the time. I want you to hear Stephen's loud voice also. So, so that's going to be great. It's really going to create some diversity, and it's going to be a lot of fun. Oh, Stephanie Muller is here. It's my girlfriend. Oh, nice. So we're going to have a lot of fun today. So today's topic is going to be physics. Okay, Stephen, are you familiar with physics?
Very little.
Very little. I'm a microbiologist, so my my brain and physics are not necessarily compatible with each other. But I'm hoping that tonight's guest will be able to clarify things for us, and that we will all become physicists by the end of tonight. And I also want to remind you guys in the chat, ask questions /Q. We're also going to open the cam slot later on. So, I really want this to happen. I want people to jump on here and ask questions and, get FaceTime with the scientists, because our goal here on Science Unplugged, which is sponsored by the Alan Alda Center for Communicating Science at Stony Brook University, the job here is for you guys to feel like you are the scientists. We want you to feel like you are in the know, and you're going to get have access. Excuse me, I can't even talk right now. You guys are going to have access to all the cutting edge research and technology that is out there today. So, my first guest tonight is a PhD candidate in the department. His name is Colin West. He's a PhD candidate in the Department of Physics and Astronomy at Stony Brook University, and he's actually a research assistant at the C.N. Yang Institute for Theoretical Physics. So he's a theoretical physicist. I don't really know what that means. Stephen, any idea?
I assume he does a lot of math.
He's calling in right now.
Hey, Colin.
Hey, guys.
A little premature there on my
Hey, it's the shortest hold time I've had on the phone in my life, I think. I'm thrilled.
I just want to put a plug out there too. Colin is an extremely smart gentleman. He, in fact, is going to be on Jeopardy next week. So I don't know if I was supposed to say that or not, but everybody, the world knows right now. And by the way, we are broadcasting around the world. Just so if you're in the chat, just tell us where you're from. because we want to know where we're broadcasting to. So good morning, good afternoon, and good evening to wherever you're from on planet Earth. We are people of Los Angeles, Seattle, Texas.
Wouldn't that be cool if we get someone to call in from the space shuttle? Space station. That's our new goal. Call in from space.
Brisbane, Australia. Wow, look at that. We got people in Ontario.
Someone says it from Mars. I think they're lying about that. I know there was big announcements about life on Mars recently, but I don't know that we got that far.
Okay, so let's get down to business. Colin, I introduced you as a theoretical physicist. Now, I hope you can provide some clarity to me and Stephen and the rest of the people in the chat. But before we dive into what it is that you do on a daily basis, tell us, what is your educational background? How did you get interested in science in the first place?
Sure. I got interested in science by the same way I think a lot of people did my age growing up, by like watching Bill Nye in school, right? And reading books by Stephen Hawking, stuff like that. I got really hooked on science at a pretty early age. And so I studied it when I went to university at the University of Colorado. I studied physics and applied math. And discovered that all the amount of physics you can learn as an undergraduate really just scratches the surface. So I wanted to keep studying that, and I've been doing that now as a PhD student for the last 5 years or so. So yeah.
It's a long process. Can everybody hear us okay? I just want to make sure
yeah.
No, I just want to make sure people in the chat too can hear us. If you can hear each one of us, yep, everybody can hear us good. All right, perfect. Okay, so you went to University of Colorado, right? Is that what you said? University of Colorado. And you studied physics and mathematics, and then you came to Stony Brook, been doing your PhD for the past 5 years. You're hopefully going to defend soon, hopefully. You'll be Dr. Colin West pretty soon.
That's the hope, as soon as possible, yeah.
That's the hope and dream of every graduate student doing their PhD. So what is it about theoretical physics? What do you do as a theoretical physicist? Define that for me.
Sure. Well, Stephen was pretty close when he said it just means I do a lot of math for a living. There's something to that. I do a lot of math, and personally I do a lot of programming because sometimes math gets so complicated that I just need to ask my laptop to do it instead. Another way to define it would be that I'm a physicist who doesn't really know how to handle tools of any kind. I've never really built anything in my life to do a physics experiment or something like that. I sit around and try to think of things that might motivate other people who are good with their hands and good with equipment to do an experiment. I try to think up new ideas for them, or predictions for them to test, things like that, very broadly speaking.
So you can see into the future sort of through the work that you do. You make the prediction. You decide whether the experiment could or could not work, right?
That's what we hope. Yeah, our goal is to tell people what should happen if you do a particular experiment, if we're right about some new law of physics or some new property of the universe, and then we rely on the experimentalists to actually go out and try to prove us right or wrong, something like that.
So in theoretical physics, there's many different aspects to physics. Are you studying like the physics of like gravity and planets rotating around each other, or are you studying a different type of physics?
Yeah, you're exactly right. There's lots of different subcategories of physics, and these days everybody's got pretty narrow specialty, and mine is quantum physics and quantum theory, like basics of quantum theory. And so certainly for me, it's about the opposite of studying big planets rotating around each other, that kind of thing. I'm interested in the small particles and how they interact with each other on a really small level.
So what is quantum physics?
Quantum physics is the study of physics between things that are about the size of an atom or a molecule interacting with one another, something like that. It's the physics that kicks in when the objects involved are really tiny, too tiny to see even with a microscope.
So are we talking like, like a molecule of sugar, like a glucose molecule? Are we talking like maybe about a carbon that's in one of those glucose molecules? Are we talking about an electron or like?
Absolutely, yeah. The smaller you get, the more important quantum mechanics is. So a glucose molecule is probably kind of right on the edge. I'm not a biochemist, I'm not an expert, but I think it's big enough that we still have trouble seeing the quantum mechanical effects in something like that. Certainly when you get down to the scale of small individual atoms or molecules that only have a few atoms in there, like water only has 3 atoms, then you've definitely got quantum mechanics going on. There's quantum mechanics going on in everything. There's quantum mechanics even going on in you and I and in large size objects. It's just that the effects get smaller and smaller, harder to see and less significant the larger the object gets. So you don't notice them until you get down to the level of let's say individual atoms or small collections of atoms.
So what is it about the physics of these really small atoms that differs from the physics of like me driving in my car?
Sure. So first of all, I should say, technically, there's nothing different. Like I was saying, all of us experience the laws of physics, and all of our full-size objects are subject to the laws of physics. So they're not special laws that only apply to small particles, just that you only notice them in terms of their effects on small particles. Just because the effects are too small, they kind of get averaged out over all the atoms in your body. So it's not going to affect, as you said, you and your car. But it turns out that if you get down to the scale of an individual atom, a lot of things about the universe seem to change. All kinds of new properties appear, and objects begin behaving in ways that we just never would have dreamed of. The three most important is that it turns out that these objects are sort of fundamentally kind of random. Not all physicists agree on this, but at least in practice, they behave like they're fundamentally random. They sometimes will change their state in ways that no one could predict ahead of time. They're capable of being entangled with one another, which means you can have particles and objects that are far away from each other in space, but still have some kind of deep connection between the two of them. You can't really understand one without understanding the other. And then there's something called superposition, which is maybe the most famous, most important property of quantum systems, is that a real-life coin can only be, say, heads up or tails up, not both at the same time. But if you shrunk a coin down to the scale of quantum mechanics, a quantum coin could be heads up and tails up at the same time. We call that a superposition of heads and tails.
So you're getting a little ahead of me here, and
Sure.
I just want to point out that Mrs. West is in the room as well.
Is she showing over there? That's great.
Colin is a newlywed. You see, we've added sound effects to the show now, so we're going high tech.
High quality stuff.
It's off my phone. I'll stop that. So Joe Anderson asks, does quantum physics affect our everyday lives? And before you answer that, I want to encourage everybody /Q, ask questions. We'll put them up on the screen. This is a conversation. This is not, we don't have any set format or anything like that. We want you guys to be driving the conversation here, getting your questions answered, and really building your curiosity. So what about Joe's question?
Sure. I would say absolutely, yeah. We may not be aware of it a lot of the time. In fact, we're just learning these days a lot of the ways that quantum physics affects our everyday lives, but a surprisingly large number of things in the world rely on quantum physics. A lot of the stuff that goes on inside any kind of computer or processor, we're discovering lately, it does depend to some extent on quantum mechanics, high-tech stuff of all kinds. And actually, a lot of nature depends on quantum mechanics, we're starting to discover. The big thing recently is folks have realized that plants, when they perform photosynthesis, when they manufacture food out of sunlight, actually rely on quantum mechanical properties in the atoms inside their leaves. And they wouldn't be able to produce the food in the way that they do if it weren't for that. So it's going on all the time and affecting us, and we're sort of just now discovering how much that's true.
So that's a good point in that, we may have just recently discovered quantum mechanics, quantum physics within the past 100 years, maybe 80 years. So what would you say?
100 years is probably a good ballpark for it at this point. Yeah.
But nature has known about this for a very long time, and that evolution has really figured out a way to integrate this into living things, right?
Yeah,
how chlorophyll has used for plants to generate energy. That's awesome. So we talked about, you touched on briefly about the different properties that a quantum particle can have, right? An atom, right? And we talked about, let's go through these one at a time just so that everyone has a clear understanding what we're talking about. Because this is like spooky stuff. Like this is ghost story type stuff, right? It doesn't make sense in the real world, but it's very
counterintuitive, yeah.
But it's real. Like we can test it. So you mentioned superposition. What is superposition?
So superposition, it's not like a really good position, but it comes from the word superpose. I mean, like imposing two things on each other. Yeah, exactly. Like that is a superposition for you, Pete. But it's not what physicists mean when they say that. It kind of means two things or two or more things at once, and it refers to the fact that quantum scale particles and objects can have two seemingly mutually exclusive properties at the same time. I mentioned earlier, you and I would think of a human scale coin, something that's not classical size, quantum size we call classical. You and I would think of a classical coin as being able to be heads up or tails up, but it would seem ridiculous to say that it could be heads and tails up at the same time. And a quantum coin could be in a superposition of heads up and tails up, so you could reasonably say that it was both, even though that doesn't make sense to us from our day-to-day intuition.
So it's like if you're on, so we're on opposite sides of town right now. So it's like you're going to be in your living room, and you could also be in the room that I'm in at the same exact time. Would that be a good analogy?
Yeah. If I were a quantum me, I could do something like that, probably. Yeah.
That's pretty crazy. So we're going to jump to one of the other questions here. Mr. Wonderful asks, is that the Mr. Wonderful from Shark Tank? I don't know.
I hope so. So I have some proposals for.
Can you explain what virtual particles are and where do they go? Where are they coming from?
I can have a stab at this. Yeah, virtual particles are a little bit outside of what I work with on a day-to-day basis, but I know there's something that a lot of people hear about when they hear about particles and quantum physics and that kind of thing. It turns out physicists sort of don't really think in terms of particles when it comes to the universe anymore. We think that most things are actually most naturally described as waves in some kind of field. And a particle is a particularly localized type of wave or something like that. The way that if you went to the beach and you watched the waves rolling in, you kind of see specific peaks that seem to move across the water, even though nothing is actually moving towards you. The whole sea is moving up and down in weird ways and that kind of thing. So when we describe these particles interacting in terms of waves, sometimes you get interactions between two different types of wave particles that are not, they don't obey all the rules that they have to in order to exist stably on their own. They only kind of exist as an intermediate mathematical object, a part of the motion of the waves, but not a freestanding particle thing that you'd see in your own. So when we call something a virtual particle, we mean isn't ever going to exist as its own kind of real world thing. It's something that looks like a particle in the equations, in the wave behavior as other particles interact.
So you talked about superposition being how a particle can be in two places at the same time, right? Mm-hmm. So that's interesting, but
yeah,
how can we use that in everyday life? Like, other than observing that, what application does that have?
Sure. So a really popular one, and one that I'm particularly interested in, is harnessing this as a way to build better computers, and not just like a little bit better. Sorry.
Did you just say better computers?
I got your attention, didn't I? Everybody wants a better computer.
So I've been playing sound effects off my cell phone here, right? This is like my bread and butter, and this is the latest model, the 6S Plus of the iPhone. This is pretty fast. Are you telling me that this is not that fast compared to what quantum physics can do for this?
It's not quantum fast. It's nowhere near quantum fast. I should warn there that I'm promising something that hasn't been invented yet. It's been studied, and like we're hoping we can build them. But the predictions of how good a quantum computer would be, they would just be off the charts compared to the old-fashioned stuff that's come before. And it comes from harnessing superposition.
So tell me how quantum physics is going to make computers better, and what is different from a quantum computer than our everyday computers today?
Sure. So let me give you the best explanation I can, and then I might have to tell you that part of it is a little bit of a lie, and I'll correct it once I've
lying to me already, Colin. Oh, God.
So a regular computer stores and processes information in a bunch of little switches, little magnetic switches in the hard drive or in the memory, right? And whether the switches are on or off is the code that they use to store the information. It's called binary code. Probably a lot of people are familiar with that. So a set of switches that are on, off, on might represent one number, and on, off represents a different number. And so for a regular classical computer to think about a sequence of new different numbers, different instructions, different pieces of data, the information maybe that describes the pixels that are going to load in a video game or a movie, it can only think about them sequentially. Like it physically has only a certain number of switches in its memory, and once all of them are in some state, the computer's thinking about some type of information, and if it wants to think about something else, if it wants to load the next bit of data, it can only do that by overwriting the previous data in some way, right? Its active memory can only have so much
one thing at a time, essentially.
Yeah, exactly. Once you got the switches set, that tells you what your computer's thinking about, and if you want to think about something else, you got to change the switches, and then
it can't walk and chew gum, essentially.
Exactly. How many of us can, right? But a quantum computer would be really good at walking and chewing gum at the same time. It would be really good at any of these things, because a quantum computer would have switches that were made not out of full-scale magnetic switches, but maybe individual atoms or something like that. Something small enough that they obey the rules of quantum mechanics, and that means, for example, they have access to the power of superposition. So one of the switches in the memory of a quantum computer doesn't have to be on or off. It can be on and off in a superposition at the same time. So I can load some piece of information into the memory of my quantum computer by putting switches in a particular configuration. And if I want to load an additional piece of memory into my quantum computer, so I can think about both at the same time, I can put the switches in that state and still have them in the other state at the same time as well, right? But they're just in a superposition of this. And if I want to think about a third piece of information, I just put them in yet another combination. I have a stack of 3 different positions that the switches are in, and so on and so forth. So it's almost as if the computer is thinking about all the information at once, rather than having to sort through it one at a time.
So Colin, I have a question for you.
Yeah.
And I'm going to say, first of all, that my knowledge of supercomputers comes entirely from TV. So I apologize if this question doesn't make any sense.
No, please.
I was thinking about you and your work with quantum computers last Monday. I was watching one of those night, crime TV shows, the one with the super geniuses who solve crimes for Homeland.
Sure.
And they had to go and involve breaking into a supercomputer center, and they actually were talking about quantum computers. And I'm just kind of curious, how much of what they described is actually correct versus, television hype? So
that's a good question. Sorry, go ahead.
Do quantum computers actually exist yet? They said that there are only 6 in the US. Is that at all true, or?
That's probably about right, and it's open to debate as well. I will say, yes, they exist by the barest of technical definitions. The size of numbers that a quantum computer can think about right now is limited to, say, something like 32. You know what I mean? Any number bigger than that is bigger than most quantum computers can handle. That's obviously really bad, right? That's everybody's most ancient calculator can think about numbers way bigger than that. So from at least one perspective, they almost don't exist, right? If they're that bad, they might as well not exist. At the same time, the important part is that they really are doing quantum stuff. You know what I mean? It was probably like there must have been a time in this country's history where cars technically existed and like 10 people owned them and they could go, or like there was a time when airplanes technically existed, but they were only owned by the Wright brothers and they could only fly for 30 seconds at a time, right? In some sense, that's almost as though we didn't have airplanes, but in a different sense, that means we've cleared the first hurdle. Like now that one exists that can do something, now it's just a matter of making it better rather than actually making it exist in the first place.
Yeah, and that's an important first step, right? Because I mean, if the Wright brothers never flew their plane, we wouldn't.
Exactly. Yeah, everybody remembers the Wright brothers. Nobody remembers the guy who figured out how to go from 30 seconds to an hour.
So I just want to remind people in the chat, don't forget to ask your questions. We have them here lined up on the side. We're actually going to open up the cam in a little bit, so we encourage you to jump on cam and ask Colin a question directly. And also, feel free to tell a little bird, tell your friends on Facebook, share this link, get it out. Let's fill up this room. We want to make sure that Blab and the internet knows that this is where science is. This is where you get firsthand access to science. And if you like what you're seeing, give our scientists some props here. Colin wants to feel some love.
It doesn't happen very often in my day job. I had to look up what props were.
Show Colin some love if you like what he's saying. I mean, the guy is going to build a computer that is going to destroy the speed of our smartphones. So that deserves a little bit of respect, I think.
I wish, Peter. I wish.
So the other thing that the show said about the computer, that they use lasers. Are lasers at all involved? Is that like they're
pretty common? Yeah, it's one of the most common ways of trying to build a quantum computer right now. Something that's really difficult about the reason why our quantum computers right now are so limited and so impractical is because the theory behind it is quite good. We know what a quantum computer should look like in order to work really well, but it's really delicate. So something I didn't mention, and I'll want to get into a little bit more, is that some of these effects, these quantum effects like superposition, they can only exist in a quantum object that's completely isolated and an object that's not being observed and not being interacted with, that kind of thing. And that's difficult to achieve, right? Everything in the universe is interacting with everything. You and I, we don't realize it, but we're being bombarded by air molecules right now. We've got neutrinos streaming through our bodies from outer space. All kinds of stuff is happening. to get the atoms in the memory of a quantum computer isolated, stable, controlled, you have to work really hard to hold them in place. And one of the ways they do that is with lasers. If you shine enough lasers at the right angles around an atom, you can trap it right where it is and hold it stable there.
That's really cool.
Do that to a bunch of atoms together, you've got a quantum memory.
So,
That's so cool.
Jeff wants to know, what can we do with a quantum computer? I mean, so I'm a microbiologist. I study DNA and proteins and trying to figure out the structure of proteins and stuff like that. Can a quantum computer help me with that? Or can it help Jeff in his everyday tasks?
It's probably a long way from helping people in everyday tasks, but any kind of scientist is likely to benefit from a quantum computer someday, and soon, probably after that, probably everybody will. Quantum computers, let's see, how shall I say this? Right now, we know of 2 or 3 major types of math problems that a quantum computer could do enormously faster than a regular computer. And I say types of math problems. There are lots of specific sub-problems underneath that. There's lots of things a quantum computer could do faster. There are other things that we don't know whether a quantum computer would be better at, but we're pretty hopeful that we'll continue to discover new ways, because the quantum computer would just be so fundamentally different in its structure and operation than a regular computer that it would open the world up to all kinds of incredible new
What are those 2 things that you mentioned? The 2 kinds?
The 2 most famous ones, and the third is more technical, so I'll leave that out. The 2 most famous ones are searching for information from a database. So when you have, for example, finding a phone number in reverse, right? If somebody tells you, just today I got a phone call from Poughkeepsie, New York, a number that I didn't recognize, right? And I wanted to know if I should answer it. Because obviously somebody wasn't a caller ID. I didn't know if it was some guy who's going to try to scam me with a free trip to Tahiti, or if it was a friend of mine whose number I just lost. And unfortunately, right now, there's not a good way for you and I to do that, right? You can't. If I have someone's name, I can go to the phone book and it's organized and alphabetized and I can sort through it. But if I have someone's phone number, technically I could sort through every number in the phone book till I found it, but that would take me.
That sounds miserable.
Yeah, it's not a good idea. And you could ask a computer to do it for you, but to be honest, a computer's not going to be able to do it much faster than you are. Basically, a computer's only going to be able to take the exact same approach as you and just start checking every number until it finds it. It'll just be able to do it a little faster. A quantum computer, because it could store all this information in its memory kind of simultaneously, can do it a lot faster. When I say that it's storing the information simultaneously, this is where I said I was lying just a little bit earlier. That makes it sound like it should be able to find the number it's looking for in just one step, right? Like it's thinking about everything at once. It should just know right away. The more information it holds in its memory at once, kind of the fuzzier its understanding of each particular piece of information is. So it can't know all the details about everything it's thinking about, but it can kind of get a rough picture of them, and then it can start discarding the unimportant pieces in big categories until it's only left with the piece that it needs. And it can paw through a database and find the thing that you're searching for, even if it's an unsorted database, a lot faster than a regular computer.
So JD,
you're building
that was category 1. Yeah. Yeah, so we'd like to put Google out of business. That's one of the things we'd like to do, which is why Google perhaps has been starting investing in quantum computing technology. They want to stay out of the curve.
JD wants to know, what is particle spin?
Oh, that's a great question. There are 2 ways to think about particle spin. One is that most particles are basically like little magnets. They have a north and a south pole, like a little bar magnet, and that means you can kind of tell their top from their bottom in a loose sense, or at the very least you can tell kind of what direction they're pointing. And spin, it's a weird word for it, but we use it to refer to sort of what direction is this little magneticness of the particle pointing. A maybe more precise way to define it is just to say it's a property of a particle, right? We've gotten comfortable with the idea that a particle can have a property called mass and a property called electric charge, maybe. But if I ask you what that is, I don't think anybody can give a good explanation to that either. I don't know physically what the electric charge of a particle is. It's just like a number that's attached to the particle. It's just a number that's stapled to that point in space. And spin is just another one of these numbers. This point in space has some property called spin, and it interacts with other spins in a particular quantum mechanical way.
Val, why don't we open up the cam spot too? We can still ask the questions from the side. So if you guys still have questions, just type in /Q and we can see them on the side, but we're going to leave the cam spot open in case anyone wants to jump in and ask Colin a question directly too. So I encourage you guys to please jump in and Ask the scientist. That's what he's here for, right? Oh, wait, right away we got Mr. Wonderful wants to come in and ask you a question. What's going on, Mr.
Nice.
Wonderful? Oh, we can't hear you. Can you guys hear him?
I can't hear him.
Hello? Can you hear me now?
Oh, there we go.
Sorry.
There we are.
Great, amazing chat. Yeah, you always hear this thing about quantum mechanics that nothing exists until you look at it. And I'm always, what does that even mean? And I'm always, I don't know if that's true or not, you'll tell us, but I'm always fascinated by the, you have all these trillions and trillions of electrons and particles, and if you don't look at something, if something is there when you look at it, and then when you don't look at it, and when you look at it again, your same situation is there. So if this is true, how do all these particles get back together in the same configuration when you don't look at something, and they slip back to the same configuration when you do look at it? And I mean, that's what people say. It's nothing exists until you look at it in quantum mechanics. I was wanting your take on that. Thank you.
It's a great question. It's a fundamental, really important part of quantum mechanics. I would rephrase that just a little bit. That sort of properties don't exist until you look at them, or properties aren't precisely defined until you look at them. And that's because, and maybe that's what you meant. But it's not quite the same thing as this kind of philosophical, poetic, like, I'm not looking at the moon right now. Does the moon actually still exist? I'm pretty confident that it does, even in terms of quantum mechanics. But this is because of this idea of superposition. A quantum switch that's in a superposition of on and off or something like that can only be in that superposition if I'm not looking at it. And once I do look at it, if I specifically check to see whether it's on or off, I'll always see it only in one of those two states. So that's sort of more precisely what they mean by that. I don't have to commit to saying that it's on or off until I'm looking at it. And then once I am, then it's one or the other. The reason for this is open to some philosophical debate, and definitely some of the questions that surround this, I would say, are more philosophical than actually matters of physics. But to a physicist, I think we've started to get a good grasp on why this is, and it started to spook us not quite as much, because what we've realized is basically, if I look at something, if I'm going to observe something, study it, interact with it, I'm going to have to affect it in some ways. I'm literally going to have to interact with it. If I want to look at something, I have to, for example, bounce some light off of it and have that light come back to my eyes and that kind of thing. If I want to study some particle, I'm going to have to let the particle slam into one of my detectors so that I can study it, right? And as I said, the superposition thing is a uniquely quantum property. It only works on objects that are subject to quantum mechanics, a scale of an atom or more. So once your object that's the size of an atom or so runs into your big laboratory device that you're going to use to look at it, then the whole system is not quantum mechanical anymore, right? Suddenly you don't have an object that's only the size of an atom. You have a whole collection of things that collectively is not the size of an atom anymore. So the atom kind of gets incorporated into the system of whatever equipment you're using to study it, and that equipment is no longer eligible for these quantum properties. It's too big to manifest these quantum properties. So the superposition, or whatever quantum property you're talking about, the technical term is it gets decohered down into a more classical situation. So as to whether or not what the object's properties are when we're not looking at it, there's still some debate about that. That's a very important question.
Do we live in a quantum computer?
That's also an excellent question. I literally did see a paper about this, a serious paper the other day, asking how we might be able to tell if our universe was a computer or a quantum computer, if we were in the matrix, whether we would be able to detect some of the glitches on a large scale or something like that. That is far outside my area of expertise, but who knows?
Thank you very much. Awesome blab. Thank you very much.
My pleasure. Thank you.
Thanks a lot, Mr. Wonderful. Mr. Wonderful was the perfect example of how we want this to work. You jump on here, ask your question, chat with the scientist a little bit, get an answer, and then free up the spot and let the next person come in. So, the cam seat is open now. Thanks a lot, Mr. Wonderful. That was awesome. I want to go to Science Joe had a question here. Some people say quantum mechanics means that you can make stuff happen by thinking about it. Is that true?
I'm trying to decide whether to be politically correct or just blunt here.
I'm going to be politically correct.
Blunt all the way.
We're not politically correct.
In my opinion, there's a lot of junk that's said about quantum physics, or at the very least, stuff that is said which is attributed to quantum physics and has no backing in quantum physics. I don't know, philosophically, religiously speaking, maybe some of these things are true, but they're not supported by quantum physics. Where this idea comes from is the thing that Mr. Wonderful was asking about. It's true that in the world of physics, it seems that our observing something can cause it to change. Only when I look at a particle does it specifically become up or down or something like that, right? So when you look at that from the outside and don't think about the technical details, that feels like a magical power of thought, right? Our looking at it influenced its behavior. But the more we've understood about why that happens, and the more we've understood the properties of decoherence, physicists have become comfortable with that, and we just think it's a regular part of the way the laws of physics work, that when we're observing something, it can't manifest its quantum properties anymore. And it's not anything as exotic as us being able to telepathically influence it with our thoughts.
We just lost JD. So JD.
Yeah, sorry, I went on so long there, JD. I didn't mean to prevent you from asking questions.
JD, call back in if you can. Maybe he had to jump out of the room for a second or something, but hopefully he'll call back. In the meantime, though, I want to ask you about another property of quantum particles. So we talked about super. Sure. Oh, actually, I'm going to hold my thought. I'm going to let JD ask.
Great.
Let's see. JD, are you JD from the Blue Streak Science podcast?
Well, how did you guess, Science Peter?
This is my friend JD. He has a podcast called Blue Streak Science. It's a website, bluestreakscience.com. I'm going to give him a good plug. And I've actually been on we have one coming out pretty soon.
We do. In fact, the next episode I'm going to drop is an interview with Science Pete, and it's on the title is The Rigors of Peer Review. So
nice. Wow.
Cool. That's kind of a basic question, right? Peer review. Everybody talks about it, but we really want to know
what does it mean? How does it work? Absolutely.
What it is. So, hey, I got a question for
you. Figure it out. Explain it to me. I'm still struggling with it a little bit.
Ask Pete. So I got a question. And so I've read a few articles recently on the possibility that the human brain may employ quantum mechanics in some way. Do you have any opinion on that at all? It's really on the edge.
Yeah, I haven't read these articles, and so I can't comment on that with real specificity. I do know of a lot of research about the role that quantum physics plays in various biological processes, including some neurological ones. I remember, I do know, for example, there's pretty good evidence that birds, part of the reason birds are so well able to detect what direction north is and navigate when they migrate may be because of some quantum mechanical properties in their brains interacting with the Earth's magnetic fields. There's pretty good evidence that some of the effects we've seen.
There was a paper recently on that specifically, actually.
Nice, I see. That's good. Maybe there's even better evidence on it now. I'll be excited to check that out. So I don't know personally about the evidence of what's going on in human brains, but I would say, in my opinion, because I know that it's involved in many biological processes and in other animals' brains, most likely, I would be astonished if it wasn't in some level involved in ours.
So there may be in the United States 300 million quantum computers right now.
That's true. I think whatever is happening in our brain that processes thoughts is probably on the scale of stuff that's too big to be quantum mechanical, right? But who knows? Somebody asked me in all candor once. There have been a few famous mathematicians and physicists over years who we just think are such geniuses. They think so outside the box and come up with things. They have this intuition for numbers that the rest of us don't have. Somebody asked me in all candor whether one of them might have had a quantum brain instead, and maybe that was how it worked.
Well, speaking of quantum brains, I did see Leon show up in here, so I'm going to step out and and hey, Peter, great blab, man.
Thanks, JD.
Awesome. All right, take care, buddy.
Take care. So while we wait for the next person to jump into, here we go. So this is Leon. Leon is actually a chemistry teacher in Pakistan. So he's coming. He's a riot, and I know he has been itching to ask you questions. He's been telling me for a long time. Leon, because he's on that side of the globe, though, his connectivity may be a little shoddy. So we may have to bear with him in the meantime. But until he logs on, and Leon, you may have to close out and then come back on. Yeah, I think he's going to do that. So in the meantime, though, I wanted to ask you about, and actually, Stephen, I forgot to make you a host, but I think I just did. And I think I did
I think I went through.
For the Eleanor. Oh, here we go. Let's see if Leon is coming back in. And, are you guys opposed to going maybe like 10, 15 minutes extra if we need to?
It's okay with me.
Val, Val can give me the heads up on Facebook.
I guess I should ask my wife, but if she's here, she can log in and tell me when it's
You can just wander into the background.
She pop up in the video and ask me a question. How come you haven't? How come you're not done?
Leon is having a little connectivity issue.
Apparently, it's fine with my wife. That's awesome.
That's fine. He'll keep working on it, but the camp.
Sorry, Leon. Keep trying,
guys. So anyone, guys and girls. Come in whenever you want and ask Colin a question. So we touched on superposition and how being in two places at the same time, or having these two identities at the same time, can allow us to develop supercomputers that are far superior to what we have today. But there are other properties of quantum particles as well, and one of them is entanglement. Can you tell me what quantum entanglement is?
I can try. I'm still working on. I've spent years trying to think of the best way to explain this, and I'm still making progress on it. So two quantum particles are entangled if you cannot understand all the properties of one without also knowing something about the properties of the other. And this is a uniquely quantum mechanical thing. That's not even the entire complete definition, but it's a good start. So sometimes the picture I have in my head when I imagine two things that are entangled is a pair of coins that are glued to the end of a tongue depressor or something. One coin can be, two coins that are not connected to each other can be heads up at the same time, or heads and tails, or tails and tails, right? But once I've glued two coins together, they're either heads up at the same time or tails up at the same time, right? That's kind of half of what entanglement is. I can have two particles that are physically separated in space, but their properties are correlated with one another. If one particle turns out to be in an upward pointing spin state, then the other one will also be, or something like that. But because of the randomness, the superposition of quantum mechanics, it becomes more complicated. In addition to being always heads up at the same time or always tails up at the same time, quantum coins could be exactly the same mixture of heads up and tails up at the same time, or exactly the same opposite mixture or something like that. And the randomness that comes from that creates some mysterious connections between the particles that you can only see in a quantum mechanical way. For example, suppose you have two quantum particles, quantum coins like this, that are entangled such that either they're both heads up, they're both heads up and they're both tails up in some kind of superposition. As we mentioned earlier, when you look at something in superposition, when you measure something in superposition, you interact with it, it becomes no longer quantum mechanical. It has to pick one of its states to fall back into. So if I have one of these particles and I look at it and I check and I see that it's heads up, I instantly know that the other one is also heads up, right? Even though I haven't looked at it yet, because I know they're entangled together. And that is true even if that other particle is not nearby, but maybe I've sent it by mail off to my colleagues in Switzerland or something like that. It will still suddenly be the case that now I know it's heads up, even though it wasn't before. So those kind of mysterious connections that can exist between quantum particles allow us to do things with them that you can't do with everyday objects.
I want to also, Leon was trying to get on before, but anyone else can jump in. Oh, here's Leon again. Let's hope this works.
Third time's the charm, I hope. Yeah.
There we go. But there are some people in the chat that are asking questions too. And if I don't get to it and there's a cam spot, just jump on the cam and ask the question directly. Oh, Leon is still.
I see a lot of good questions out there. I know we're not going to get to more than a fraction of them, but I want to tell everybody all the ones I've seen have been really cool.
So while we wait for Leon to get his internet working, I know he's probably banging his head against the wall. Toby asks, how do we study things at a scale this small?
That's a great question. There are a lot of different techniques. One of them is with lasers. To go back to what Steven said earlier.
Everything's better with lasers.
Everything is better with lasers. It's true about Star Wars. It's true about physics, right? Yeah, exactly. The wonderful thing about lasers is lasers are wonderful things, and in particular, lasers emit only a small handful of photons, particles of light at a time. Right, a light bulb just splatters photons everywhere, but with a laser, you can control it so that only a few photons come out. And photons are quantum scale particles. It doesn't even really make sense to talk about the size of a photon, but it's certainly smaller than an atom, you know. And so when you hit an atom with a laser, you are hitting it with something small enough that it can study its quantum properties, right? To study something, you sort of need a tool that can reach down to the size of it, right? If you want to build piece of furniture, you can use a hammer. But if you want to build a tiny model thing, you're going to need tweezers because the tool has to be the size of the thing you're trying to build. And if you want to study atoms, you need something that can reach down to that size. And so we use things like lasers, we use beams of individual electrons, things like that, that we can control and generate from a big human-sized source, but that reach down to the size of small stuff to interact with these individual atoms, stuff like that.
So I'm going to jump to Leon's question here because I don't know if he's going to get
Sure.
it.
Yeah.
He asks about decoherence and Copenhagen interpretation.
Those are some big words.
Those are big words, yeah.
Leon must know what he's talking about.
Leon wants to jump right into all the controversial parts of quantum mechanics. This is this goes back to what was being asked about, I think, by Mr. Wonderful. I've forgotten who now, about how do we understand what's going on in a quantum system when we don't look at it, and what does it mean?
There's Leon. There's Leon right there.
Nice.
I'm on my wife's computer. So I'm like,
nice.
Hello, Colin.
Good to see you, Leon. How you doing?
I'm gonna try to keep my shorts dry, and I'm gonna try not to fanboy too much right now. And I'm just gonna breathe. But
please, because I'm not worthy of anything like that.
He's back.
Nice.
Until my connection dies.
Sure.
Again, back when I really read this stuff when I was in uni was in the late 80s. And the Copenhagen interpretation and all the weirdness of quantum was being connected to consciousness. It's like if a consciousness observes it, then, there's the collapse of the wave function. Science Pete sort of schooled me a little bit where he's saying, no, the observation is simply another quantum, something at the quantum scale gaining knowledge, meaning knowledge in the sense of, if it goes through the slit, well, whatever detected which slit it went through had to interact at the quantum level. And as soon as the wave collapses, we're no longer into quantum weirdness. Now we're into the macro. It was there and it measured and it acts like a particle and stuff.
Pretty good description.
Yeah. Can you describe the current state of the art, so to speak, of what I would call the Copenhagen interpretation? And in other words, what is the modern interpretation of measurement and how does that connect to consciousness?
Sure. So I can't give you the definitive modern interpretation. There's still a debate on this, and there are still different schools of thought on how we should picture what's going on in quantum systems. Some parts of it are beginning to become clearer than others or more accepted. And I would say your description of what you described, which is what I called decoherence earlier, is pretty close to what most of us think of. It's that you can only observe these properties when something is on the scale of an atom, on a quantum mechanical scale. I mean, these properties, not that you can only observe them, that's a bad word to use. These properties can only manifest themselves on a quantum mechanical scale. And in order to try to observe them, you necessarily involve them in a system which is too big to be quantum mechanical. You've got to use some piece of equipment. Your own body becomes involved. And the number of atoms that are all interacting is too large. The system is too big for these quantum properties to exist. So that's sort of the practical answer, that how physicists think about this is that these properties really do exist in systems that are sufficiently isolated, but it's fragile, and when it interacts with too many other objects, too many other particles, it breaks down. It gradually degrades. As far as consciousness, I don't want to go too far in being opposed to this. I'm inherently skeptical of these kinds of things because I hear it all the time used to suggest that quantum mechanics proves or demonstrates that our consciousness has some mystical properties or control over the universe. And I don't think it does that. At least I'm not aware of any good evidence really displaying that. I don't think it necessarily says anything clearly to the contrary. I just don't think quantum mechanics really has anything to say from a physics perspective about consciousness. Right. Yep. There are some good philosophical questions about consciousness that have come out of considering what we know about the world now, what we know about quantum physics. But in terms of scientific evidence and scientific theory, I'm not aware of anything that's widely accepted that connects the two.
While my internet is working, I have another question about entanglement.
Sure. Entanglement is my favorite.
So Einstein, basically, they're getting to the point where they are disproving Einstein's objections to quantum in the lab, because he always said
Yeah.
Because again, like let's imagine two entangled particles where you've measured them with enough accuracy in terms of Heisenberg's uncertainty principle that you kind of know where they are.
Mm-hmm.
And so in a sense, you know that piece of information and you're not allowed to know too much.
Mm-hmm.
But you fire these suckers off.
Mm-hmm.
You didn't measure their spin when you knew within a little tight band of where they were. So you actually knew where they were, which of course you could not know their spin because then you're in violation. So you fire these suckers off long distances, maybe years before they get detected. If you detect, again, I'm talking Newtonian logic right now, and then I'll flip it into the quantum weirdness. But according to Newtonian logic, so Pauli's exclusion principle, they had to have different spins.
Okay.
If you knew their spin and if you knew where they were, now you're in violation of the uncertainty principle. So you don't measure their spin, but you know that they're in the same place. You fire these entangled particles off. If you measured the spin of one of them, in a Newtonian logic, you would know the spin of the other because you knew where they were at one point. You would now have violated Heisenberg's uncertainty principle, which Einstein said would then debunk or whatever, cast him down on it. However, my understanding is this is weirdness now. So now we're into the weird. If you measure,
can I step in here and just ask a question as a total non-physicist? When you say quantum weirdness, I'm kind of lost. And maybe this is not explainable, but how weird are we talking here?
It's not a technical term.
Let me finish my analogy and see if you think it's weird.
All right.
If a light year in the future, you measure one of them to be spin up, in Newtonian logic, you would think the other one has to be spin down, but now you're in violation. Therefore, somehow, the one communicates to the other instantaneously, hey, I've been measured, you or me had better flip. And I think if I understand quantum, they do. In other words, just because you've measured one spin up does not mean it was spin up when it began its life.
Yeah.
And it would only have changed its spin upon being measured. This gets back to the weirdness, Stephen.
Okay, so this is sort of like the question we had before at the beginning about how the particles are, what you're observing them, they have to suddenly either be in one state or the other.
But he wants to know in particular, I think, about something that really freaked Einstein out. Part of why he was kind of reluctant to accept quantum physics, and that's
That's a cool thought. I didn't realize that Einstein didn't get everything right. That's
believe it or not, he was very slow to get on the quantum mechanics bandwagon, if at all. He, to the end of his life, was.
I've studied the biology of Einstein. He died thinking the weirdness would be explained away, that we were missing something.
Yeah, he thought the weirdness was evidence that we didn't have it right. That we were missing something, and we're beginning to discover that the weirdness is the truth of it. That there's nothing we've missed. Yeah.
So Colin,
Newtonian stuff that's weird, man. Quantum is real.
Exactly.
Translate what Leon just said for the rest of the people in the chat, and answer him in a way that we can understand.
Sure. First of all, I just want to make one little sort of correction or adjustment to what you're saying. That's a lot of what Leon's talking about hinged on. He was saying the Heisenberg uncertainty principle, which is a famous thing in quantum mechanics that says there are kind of pairs or sets of types of things you might want to measure about an object, that you cannot measure both of those things as precisely as you want. The more you know about one, the less you can know about the other, that kind of thing. And you were talking about position and spin, and actually position and spin themselves are not one of the pairs that you can't measure, but they're parts of different pairs. So position and momentum, for example, is one pair. Right. You can't know both those things at the same time. And spin, he used the word spin a lot, and I did a poor job of not describing this earlier when someone asked about spin. Spin is that technical term that someone else asked about, and it really just means like it's the orientation of the little magnetic moment that I was talking about, is that particle pointing up or pointing down, just for the rest. I know you know, Leon, just for the rest of the folks. But you can talk about spin in several different directions. You can have a spin in the vertical axis. Are you pointing up or are you pointing down? And you can have a spin in a horizontal axis. Are you pointing sideways? Are you pointing left or right? That kind of, it's not quite like that, but you can have spins in different directions, and different sets of spins, whether you're spinning vertically or spinning horizontally. Those are two properties also that have a Heisenberg uncertainty principle between them. You can't measure how much something is spinning, whether it's up or down, and how much whether it's left or right at the same time.
And this spin, the spin is important because whether or not they're spinning in a certain direction, how does that affect the bigger macro properties?
It's just a property of the particle, and it's something that we can measure. So the reason it's significant most of the time, I mean, it plays a role in a lot of things in chemistry and physics, but one of the reasons a lot of people cares about it is because it's a way of storing information. This is the way that when I talk about a quantum computer and we say, well, maybe we can make the switches in the memory out of quantum particles. Whether the switch is on or off will actually be stored as whether the particle is spin up or spin down.
Oh, okay. So at the beginning, when you're talking about the up and down, that's spin. Spin is
abstractly
think of it as just
a type of number, a property that stores like one of two states, or depending on the particle, one of different states in the particle.
Leon, we're gonna free up your cam spot because we want to cycle through people. But thank you so much.
Thank you, Leon, and I'll try to.
Thank you so much, Colin. Thank you.
My pleasure. Thank you so much.
By the way, Stephen, I'm gonna tap you on the shoulder to maybe do a Skype to some grade 3s in Islamabad who are excited about rocks.
Cool.
Yeah. So I'll through Peter, I'm sure we can connect actual emails. All right. Yeah. Thanks so much.
See you, Leon. Thanks again.
So if anyone else wants to jump in and ask a question, that's great. We got more. Actually, let's go to a simpler question here because Buka was saying, how does a PhD theoretical physicist make $1? That's a great question.
Colin, well, you're paying me for
a real dollar, not a theoretical dollar.
Are you making enough to buy at least some like ramen noodles?
Oh boy, ramen noodles. Yeah. It's funny you should ask that. Literally, what I was doing before you Skyped me for this evening was working on a job application and then eating a Subway sandwich because I needed something cheap to have for dinner. So sometimes we don't make $1 all that well. But I don't know whether this question is motivated from like you're asking, well, if I want to go into physics, what lines of work are available, or if it's more a societal question like how do they benefit society, that kind of thing. I guess I can try to answer both at once. I mean, a lot of physicists work at universities, especially theoretical physicists, because we do stuff that doesn't necessarily have an application planned. We're just kind of hunting around trying to figure out what the next big thing could be. It's harder. Fewer theoretical physicists work at corporations because corporations want you to come to them and say, I have an idea for how to build this cool new device, and a theoretical physicist is more likely to tell you, nobody really understands some of the properties of the proton. It seems like if we knew more about protons, we might discover we could build cool devices out of them. Can I learn more about the proton and so that we'll discover something? I think of theoretical physicists as like the modern day version of like Lewis and Clark kind of explorers, right? Lewis and Clark weren't sent out with the mission of like, they didn't go out there because they knew there was some nice farmland and they were going to go farm that land. They were sent there because people were like, it seems like we should know more about like 2/3 of our country we basically haven't looked at. We should probably look and maybe we'll discover some cool stuff there that we can use, maybe we'll find a Northwest Passage. They didn't find a Northwest Passage, but they found other things that they weren't expecting that turned out to be awesome.
So what you're saying is the proton is this day and age equivalent of the Louisiana Purchase.
Yes, I guess that's the metaphor I just accidentally stumbled into. Yeah, I'm not sure I'm proud of that one, but it works. Right, yeah, right.
We're going to stay on until 9:15 tonight too, because we've had so many great questions. I really want everyone to tap into your brain there, Colin, and squeeze it for all that it's worth. But also, I like that we're asking questions, basic questions like, how does a theoretical physicist make $1 too?
Sure.
Because as technical as things may get, we're natural, normal people like everybody else too. So I
wouldn't say we're normal, but we're real people.
We're slightly abnormal, I guess, in a way.
We are, on the internet at 8 p.m. on a Thursday. I think we're setting the bar real high here.
But the goal is to get the audience here to feel like they are the scientists, right? I want them to take it for a second, or at least for an hour and 15 minutes, to kind of put themselves in the shoe of a scientist, so they can kind of, understand what science is like, not to be afraid of science, and really understand where the world of science is coming from. So, so Buka also asks, any personal heroes in the field of physics, quantum physics? Yeah, who are your heroes?
Sure. That's hard. I have a lot of physics heroes in one way or another. Richard Feynman is a big hero of mine, at least as a physicist and a communicator. the stories of his personal life make me think I don't want to emulate his behavior as a person sometimes. But I think he was a nice guy, but he was a troublemaker. Feynman's probably maybe one of the best known examples, but he was a brilliant scientist, and he was extraordinarily good at explaining his scientific ideas, both to other scientists and to non-scientists. And anybody who's really interested in understanding science better and wants a nice technical view, his stuff is older because he lived back in the 60s. But his stuff is excellent. It's still a good place to turn for information about science and the introduction to quantum physics. Gosh, I have so many physicist heroes. I'm going to mention one who I think doesn't get enough press. Lots of people who know anything about scientists know about Richard Feynman. A wonderful mathematician and scientist who more people should know about is a woman named Emmy Noether. She was mostly a mathematician, but her maybe most important and significant mathematical contribution was actually in the field of physics. And she was one of the first women to be... I shouldn't say one of the first, but she was working at a time still when women were not, encouraged to enter the field of physics and not always supported seriously. And she did some extraordinarily creative and extraordinarily groundbreaking work studying the ways that the symmetries of the universe affect the laws of physics. It is really mind-blowing stuff.
Can you repeat her name for us again?
Somebody asked the spelling, yeah.
Emmy Noether. Noether is German. It's N-O-E or O-umlaut, N-O-E-T-H-E-R, I think. I hope I have that right. I'll be really embarrassed if I don't, because I just called her a hero of mine, but it's close.
Somebody who says no love for Boltzmann?
Boltzmann was cool, right? Lots of people were cool. Linus Pauling was cool. Pauling is someone who I think was a cool person as well as a cool physicist. Paul Dirac was a very influential physicist. Schrodinger, obviously. Heisenberg, not the one who sells meth, but the one who invented the answer.
Wait, what?
It's a big, not the Heisenberg from Breaking Bad. Is that too dated a reference now? It's been a couple.
So Joe Anderson asks, can you explain the cat in the box?
Oh, I was hoping you'd ask me to do this because a lot of people do, I think, a very bad job of explaining the cat in the box. I don't know if I can do a good job, but I will tell you what is not a good explanation of it anyway. Sometimes this refers to Schrodinger's cat, which is an actual thought experiment.
Who is Schrodinger?
Schrodinger was a famous physicist who was around at the birth of quantum mechanics, quantum physics, and who was instrumental in developing some of the basic ideas and the basic techniques in quantum physics. One of the fundamental formulas that we study when we first introduced in quantum physics is called the Schrodinger equation. And Schrodinger put together this thought experiment that he later said was not entirely serious, but it was intended to illuminate some of quantum weirdness. But it's often misinterpreted now. The idea behind the original Schrodinger's cat, and I gotta warn people, the story is a little dark or like a little. No one's ever actually done this. I want to clarify. We all acknowledge that it would be unethical and terrible. I want to show you something really morbid that my wife did, which is drop our cat onto the couch next to me.
That's awesome.
As soon as I started talking about this. So this is Phoebe. Phoebe says hi to everybody. And it underscores how much respect I have for cats and how you shouldn't hold against me what I'm about to describe to you, which is...
You may want to cover Phoebe's ears.
Yes, I hope she's not listening to this.
Actually, can you pet Phoebe while you describe this? That would be...
I wish. She's not fond of laps. I don't think that would go well. But
that's right.
Yeah, no, it's a good idea. But it would just make me look more evil, right? Schrodinger's hypothetical idea was, as a way of trying to understand the probabilistic part of quantum mechanics, right? An individual quantum particle can be spin up or spin down, or spin up and spin down, and we don't really know which until we look at it, right? When we're not looking at it, it's perfectly reasonable to say that it's both at the same time. So Schrodinger said, suppose I build a weird, really cruel device, which is a vial of poison and a hammer that's like poised to break the vial of poison gas, right? And then I rig the trigger on the hammer to something quantum mechanical. For example, the radioactive decay of an atom. Atoms decay. A lot of people know this and they don't realize this is a matter of quantum mechanics. Radioactive atoms decay, right? That decay is random because it's quantum mechanical. There's no deterministic way to know when any particular atom is going to radioactively decay. So Schrodinger said, get one atom, when it decays, if it decays, it triggers the hammer, it breaks open a vial of poison gas. Now put this evil contraption in a box with a cat, seal up the box, right? Is the cat alive or dead or not, is the question. And Schrodinger's answer sort of is, well, I'm not sure Schrodinger had an answer to this, but that's the question, because the point is, since I haven't looked at the atom yet, it can be in a superposition of both having decayed and not having decayed, right? And Schrodinger said, does this mean that the hammer can be in a superposition of both having swung and not having swung, which would mean that the poison is in a superposition of having been released and not having been released, which would then mean that the cat is in a superposition of being dead and not being dead? And he was just trying to extrapolate this weirdness out to a bigger and bigger scale, to try to emphasize that quantum weirdness that Leon was talking about. People have trouble picturing why it's so weird to think that an atom maybe has and hasn't decayed at the same time. But when you imagine this chain of reasoning, you get to results that are a lot more obviously weird and a lot more obviously spooky. So sorry.
I just wanted to point out that I've had my mind blown right now, because I actually study radioactive decay and didn't realize that that's actually quantum mechanics.
There you go.
So,
Yeah,
wow.
it absolutely.
I learned something.
Yeah, I think it took me a while for that to click for me also, because we're introduced to radioactivity often in like middle school, you know. But it's
I didn't learn about that.
Right? Boom. Yeah. No one knows how to predict if a particular atom in a sample is going to decay or ever. It's entirely probabilistic.
Did you just have a eureka moment?
So let me finish up saying something about the cat in the box, because as I say, this is something that people get wrong a lot. Two things or at least one thing that the Schrodinger's cat story does not mean. Oftentimes people leave out the quantum mechanical radioactive part of it altogether and still try to tell the story. They say, if you put a cat in a box and you're not looking at it, you don't know if it's alive or dead, so it might as well be both at the same time, right? And that has nothing to do with Schrodinger's cat, and that's not anything that quantum physics says, because it's missing the quantum piece that kicks off the whole chain of events. There's no reason a cat in a box is just a live cat in a box, and I know that even if I'm not looking at it, as long as I take the cat out of the box in time to feed it and give it oxygen and stuff like that, right? The only question is, what about this cat whose fate is tied to something quantum mechanical? And it's still in some ways open as a philosophical question. It's kind of like the tree falls in the forest, right? No one is ever going to be able to know, because we can't look at the cat to check, because then we'd be looking at the cat, and that breaks the rules of the experiment. But this comes back to the decoherence thing, and I would say the bottom line is we mostly are comfortable now with the idea that on a practical level, the cat is either dead or alive, because basically the cat is observing whether or not the atom decayed. The cat is a large non-quantum object who is interacting with the atom as a quantum object, and it determines if it gets rid of that quantum capability the same way that you or I would when we look at and measure the quantum thing. We've started to come to terms with that. There are still philosophical questions that remain about exactly where does that happen, or are there weird ways you can construct it so that it doesn't. But so the two takeaway points are, don't leave out the quantum piece, the radioactive piece, when you're describing this. And second, don't think that anyone's ever done this to a cat or ever would.
Phoebe is safe, and no one.
Phoebe is safe and sound. She has turned her back on me. I don't know why.
She's
not interested. Say hi, Phoebe.
So Blue Streak says eventually a smell will come from the box.
That's an interesting point. And then would we be in a superposition of both having smelled and not having smelled? Some interpretations say the universe splits there, but that's more philosophy than physics.
So we have 2 minutes left.
Oh gosh, yeah.
So I kind of want to end on. I like to end these on a bit of a wider note. Sure. And there was a question up here. It's kind of a shameless plug for me in a way, but it touches on something that, and you've done a lot of science communication. And Michael Dove asked, do we need to invest in more people in explanatory and promotional areas of science? Maybe using a science guy, maybe a science Pete, or something, or a science Colin, or a science Steven,
Exactly.
Types that have likable personalities to promote knowledge in science. What do you think about science communication today?
Sure. I think it's hugely important and undervalued both by scientists and non-scientists. I would say, and I don't just say that as a theoretical physicist who wants to make a buck and would be love to be paid to explain these things to people more often. It's important for a number of reasons, but the fact of the matter is, in the past, technology and science have not necessarily progressed so fast that people couldn't sort of pick up on them by reading them on their own, right? If you think about what happened in the Industrial Revolution, that was a major change in our technology and the way society interacted with technology, but people could comprehend that. I don't think it was beyond anybody to really get a grasp of what the cotton gin was and how, okay, suddenly that dramatically alters the economy of the South, but they could picture it and they could study the diagram and they basically understood what a cotton gin was, that kind of thing. And so when it affected political questions and issues of slavery and all this stuff that were affected by the technology at the time, people were equipped to discuss that intelligently. And I think for better or worse, we're reaching a stage when technology and science evolve so rapidly, it's understandable that people who are not experts and can't devote their whole working lives to keeping up with it, I do, and I can't keep up with it, they of course don't know a lot of the science that is behind our day-to-day technology and devices, let alone the science that affects important political questions and important policy questions and that kind of thing. And it would be great for them if people could explain it to them better, and it would be great for scientists if we could explain it better. There shouldn't be this big gulf between the science community and the lay community. I wouldn't think that it's necessary. We just need more people doing the explaining. I'm pretty convinced, if I can soapbox for one more minute, that there's still nothing in science that the average person can't understand well enough to make, educated conversation about. If they're given a good explanation, if they're given 10 minutes sitting down over a beer with somebody who has some practice explaining science. The problem is not that it's too difficult for people to grasp. It's just that those opportunities don't arise because there aren't enough people making those moments happen.
Very well said. Val is I want Val to put up our logo. If she can just hit the call in button, and there we go. So, guys and girls and everyone else around the world, we are going to be doing more of these. We're going on hiatus for the holiday break now. Our next episode will be on January 21st. So we'll start the countdown timer.
I'll be listening.
Mark your calendars. And
remember, it'll be on the other name.
Right, it'll be on the Alan Alda Center account for Blab. So, guys, I want everybody to follow the Alan Alda Center. That's there on the Science Unplugged banner right there. Follow them on Twitter. Follow me on Twitter and on Blab. Follow Steven and follow Colin too, because especially on Twitter, I'm sure that if you guys have any questions that they would love.
There have been so many good questions popping up on here, and I've been really excited about a lot of them that I just didn't even get to address. But in fact, some of them, Leon, that did get asked, I didn't get to answer. But I'll try to answer some of them.
So tweet them. You could tweet them to anybody, and hopefully, Colin would be happy to respond to you via tweet and or send you more information on what you want to know. So I started the show off with our new theme song. Maybe I should end with.
I think we need exit music.
Colin, I think you need to dance with us to the game show music.
I'm part of the crew now. I can do the head bob. This is how a theoretical physicist makes a.
This is shameless entertainment here. If you didn't understand anything about quantum physics, but you enjoyed the dancing, game show music at the end, you guys got at least some entertainment at it. So thank you everyone for joining us around the world. And as always, I like to add, keep calm and science on.
9.
Sounds good. Thank you guys for having me. Take care, everyone.